We can try to solve a system of congruences, but before we do that, we'll want to know, does a solution exist? And if so, how many? So let's start with a system of two congruences, where we'll assume that A1 is less than N1 and A2 is less than N2. Otherwise, the congruences aren't very interesting. If we have a solution, then it must be true that x minus A1 is something times N1, and x minus A2 is something times N2. And so if we subtract the one from the other, we get. Now, what can we do with this? A good starting question is often, what do primes have to do with this? So, suppose we have a prime that divides the first modulus. If the prime also divides the second modulus, then it has to divide the difference. While this could happen, it means that if a prime divides two moduli, then the corresponding congruence must have a specific relationship. Let's avoid this for now and require that the moduli be coprime. So suppose the moduli are coprime. If x equals A1, then obviously x is congruent to A1 mod N1. And as before, we can add any multiple of N1 and maintain our congruence. So x equals A1 plus something N1 will still solve our first congruence. And so we want to find k where a plus kn1 is congruent to a2 mod n2. Now, since n1 and n2 are assumed coprime, then the greatest common divisor is 1, and so we know there's some linear combination that gives us 1. So at this point, we'll do something we can do in math quite productively, which is work from the end. In this case, we hope that for some n, a plus kn1 is congruent to a2 mod n2, and so x equals a1 plus kn1 solves the system of simultaneous congruences. Now, definitions are the whole of mathematics. All else is commentary. If a plus kn1 is congruent to a2, then the difference is something times n2. Now, we know that we have a linear combination of n1 and n2 equal to 1, so let's rearrange this and get n1 and n2 on the same side and push everything off to the right. And let's see if we can get from our linear combination equal to 1 to our statement here. And we see that if we multiply by a2 minus a1, we get, and that joins the bridge. And so from our linear combination, we can find a linear combination equal to a2 minus a1, which finds the value of k and solves the congruence. And if you look at it, didn't that just prove the base case for an induction proof? So suppose x solves a system of n equals k congruences with pairwise coprime moduli. Let nk plus 1 be coprime with each of the moduli. Then x prime equals x plus some multiple of the product of all the other moduli still solves the system of n equals k congruences. And since nk plus 1 is coprime with each of the others, then the greatest common divisor is 1. Now, for convenience, let n be the product of the preceding moduli. So, because the greatest common divisor is 1, we know there's a linear combination of n and nk plus 1 equal to 1. We'd like to say that x plus rn is congruent to ak, so that tells us that the difference is some multiple. We'll rearrange it so it's a linear combination of n and nk plus 1. And as before, if we multiply by ak minus ax, we get, and that allows us to complete the bridge. And consequently, x plus rn solves the system of k plus 1 congruences. Putting everything together, let n, 1, n2, and so on be a set of pairwise coprime integers, and let a1 through ak be any integers. then the system of congruences has a solution. As we saw, it's possible for a linear congruence to have more than one solution, even mod n. So is the solution unique? So a very common strategy in math is to decide if something is unique, see what happens if there's another. So suppose x prime is another solution to the congruence. Then x is congruent to a1 mod n1, and x prime is congruent to a1 mod n1 as well, and so on for the others, but we'll start with this one. So the difference is congruent to 0 mod n1. And by a similar reasoning, the difference between two solutions is going to be congruent to 0 mod anything else, so the difference must be divisible by each of the moduli. Now, since the moduli are coprime, this can only occur if the difference is multiple of the product, meaning that difference is something times the product of all the moduli. So x is congruent to x prime mod the product. Consequently, the solution is unique mod the product of the moduli. And this means we can extend our result to what's known as the Chinese remainder theorem. The Chinese remainder problem with pairwise coprime moduli has a unique solution n, where n is the product of the moduli. We'll see what we can do with that next.